Let's get started. Good morning, everyone. Welcome to today's SNAPP seminar. We have Professor David Yao from Columbia University. Professor Yao is the Piyasombatkul Family Professor of Industrial Engineering and Operations Research at Columbia University. He also serves as co-chair of the Financial and Business Analytics Center at Columbia Data Science Institute. His research and teaching interests are broadly in stochastic systems, with a special focus on problems in resource control and risk analysis. And he has received several awards, including being an IEEE Fellow, Informs Fellow, and a member of National Academy of Engineering. So without any further ado, the floor is yours, Professor Yao, and he'll talk about square root voting today with us. Thanks.
Thank you, Shiva. It's such a pleasure to be here. Like all the other speakers before me, I want to express my sincere thanks to you and to your colleagues on the organizing committee. To say SNAPP is a wonderful activity, a great community service is an understatement. I've been asked to speak at the series for a while. I felt reluctant. Part of the reason is because I thought the speaking spot should be given to younger researchers. So in that regard, I'm happy to present today ongoing joint work with my colleague, Wenpin at Columbia. So this is very much not just a joint work, but also ongoing. I think we touched upon some problems, provided some solutions, but there are also lots of things left to be done. And I will get into these during the talk. So to start with, I want to talk about the two things. One is this square root voting, and the other is this POS, proof of stake. So first, let's get down to the square root voting. This is an idea originally proposed by Lionel Penrose, and that's Roger Penrose's father. Roger Penrose, of course, is the Nobel laureate, 2020 Nobel laureate in physics for his work, Penrose-Hawking singularity theory. For me, of course, Roger Penrose, I know the name Penrose best from this Penrose Moore Penrose generalized matrix inverse. But then it turns out that Roger's father, Lionel Penrose, was also a very, very well-known intellectual. In fact, Lionel started trained as a mathematician before he switched into the medical field, and then became very well known in genetics and also psychiatry, etc. Extremely broad. During his early years, he did quite a bit of research in mathematics, mathematical projects at least. And from my reading is that he also involved Roger in those projects. So one thing he did in those early years was what's called a Penrose method. And the Penrose method is basically this idea of a square root voting. So it was proposed, he proposed that around the end of World War II, I think around 1946, shortly before or after the UN was founded. So his idea is that each member country will be given a number of votes in proportion to the square root of its population, not directly to its proportion. Of course, this never really got adopted by any serious world assembly. But it was indeed considered seriously by the European Union in 2007 when it was trying to reform its voting rules. The idea is obviously worried that some big countries could have too much sway. There's a nice article about this, which I quoted here, which came out last winter, 21. So what's behind this idea? For us, participating in small committees at universities, I think we are familiar with this phenomenon. If you think about a committee, a small committee of 3 members, then any one of the members can cast a tie-breaking vote and then be on the winning side, so to speak. And that probability, if you calculate, it's very easy, it's 1/2. That's simply because for 3 members, the total number of outcomes will be 2 to the power of 3, which is 8. And then leave out 1 member, the other 2 members could have a tie. And the possibility for a tie vote is 2 times 2. So that's 4/8. So that's how you got 1/2. Now, if you increase the size to say 9, well, first of all, the size by definition in this case has to be an odd number. Otherwise, there won't be a tiebreaker. So if you increase the size of the committee to 9, you can follow the same calculation, and the probability came out to be a little above 1/4. So it's not a linear decrease. Obviously, once you increase the size of the committee, this probability will go down. But now the question is, how would this probability decrease as the committee size grows? The answer to that question is, in fact, pretty simple and easy to derive. So you basically do the calculation just like what I did in the case of 3 members. So if you say the committee has a total of 2m plus 1 member, then the total number of outcome is 2 to the power of 2m plus 1. And then the number of tied outcomes is you split the leave out 1. The other 2m members have an even split, 2, n, and n. And then this 2 is basically either, you have 1, 0. So there are a combination of 2. So therefore, this number over this number, the ratio is the probability we are talking about. And you can simply use the Stirling formula to simplify it. And very quickly, you get the ratio to be in the order of 1/√n. So that's a very nice result, which says that this is the rationale behind the Penrose method. All right, so now let's talk about POS, proof of stake. In order to talk about a proof of stake, I needed to briefly introduce proof of work, POW. And before I get into POW, I need to talk about the blockchain. So blockchain, as we all know, is basically a decentralized peer-to-peer network. By the way, there are 2 versions of a blockchain, the private version and the public version. I'm strictly talking about the public version. It's completely non-permission based, peer-to-peer, anyone can join. So this is a decentralized peer-to-peer network, and it's known to be a good way to do a platform for exchange, for trading, basically matching supply and demand. And underlying the blockchain, the key mechanism is actually a voting mechanism, or what's called a consensus scheme. So proof of work is a protocol for Bitcoin. So this is what Bitcoin got started in 2008. This is laid out in a paper by this mysterious author, Satoshi Nakamoto. It's a very short paper. I think only 8 pages plus 1 page of a reference. And what I quoted here is from the abstract of that paper. 3 sentences. And the 3 sentences basically laid out lots of key concepts and ideas of POW, proof of work, and the Bitcoin blockchain. All right, so let's go over this quickly. 3 sentences. The first sentence says, a network timestamps transactions by hashing them into an ongoing chain or hash-based proof of work, forming a record that cannot be changed without redoing the proof of work. So this one basically lays out the process of POW. What is POW, what is proof of work, and how is it done? So proof of work is basically to solve a hashing puzzle. Hashing, by the way, is an algorithm, an encryption algorithm. So this proof of work is basically trying to establish, to verify a transaction and put it in this right place of this so-called longest chain. Okay, so this is the proof of work. It's basically trying to solve a hashing puzzle so as to verify a recent transaction and put the transaction. By the way, the word of blockchain refers to a chain of blocks, interconnected blocks, and every block is a transaction. The next sentence says the longest chain not only serves as a proof of the sequence of events witnessed, but proof that it came from the largest pool of a CPU power. So the second sentence basically tells us what is the outcome of proof of work. Proof of work is basically to establish this longest chain. And then largest pool of a CPU power leads to the third sentence. It says that as long as a majority of the CPU power is controlled by nodes that are not cooperating to attack the network, they will generate the longest chain and outpace attackers. The third sentence, in fact, basically says, why a network like Bitcoin needs to have that proof of work process. It's mainly trying to prevent the so-called double spending attack, meaning anybody who has already spent their coin and then try to reestablish this longest chain by saying that this is, after all, another recent transaction, I'm going to spend that coin again. So this is called a double spending attack. In order to do that, the dishonest node needed to overcome the combined CPU power of all the other nodes, because every node in the network can pursue this validation of transaction. So whoever get the work done first will be able to claim they have established the longest chain. Now you may ask why anybody want to do that. Well, if they do that, they will get the coin or the transaction fee. So therefore, the validators are the so-called miners. So they mine the next coin, they earn the next coin. So therefore, in order for the attacker to cheat, to do double spending, the attacker needed to have the kind of a computing power to overtake the rest of the network. So this is basically, in a nutshell, the proof of work. The hashing algorithm, being an encryption algorithm, is difficult to solve. It needs considerable computing power, and that because every node in the network, in principle, can participate in this proof of work. So therefore, an unintended consequence of Bitcoin is enormous amount of energy required to do this, to carry this POW. Okay, so to summarize, the proof of work is basically to verify transaction, to establish the longest chain, requires considerable computing power. And the purpose is to prevent double spending attack. And in fact, in Nakamoto's paper, as I said, is a short paper, break into many short sections. The longest section, in fact, is the last one, section 11, with a title, section title called Calculations. That's where it presents the model. And if you read the model for people in our area, you will immediately recognize this is a gambler's ruin model. In fact, it's a great teaching course to teach gambler's ruin. So it concerns a simple random walk, and even the notation is what we use. And in fact, Nakamoto quoted the Fellow's classic book for that model, for the solution. So it basically concerns the probability that a simple random walk with probability P moving to the right positive direction and Q, which is equal to 1 minus P moving to the left, the negative part. And this is basically concerns when the P is larger than Q, Q being the rate computing power for the attacker, and the P being the computing power of everybody else. So this concerns whether the attacker can ever catch up, therefore hit a negative value. And as we all know, that probability decreases exponentially. So this is how proof of work is central to ensure that the validation is workable. So as I said earlier, because everybody in the network, every node can participate in this proof of work process. So therefore, the consequence is enormous consumption of energy, computing power. So proof of stake is a refinement on that. In proof of stake, anybody participating in establishing the longest chain as a validator will be selected proportionally to their holdings, their shares. And this was started by another coin, peer coin, 2012, and then more recently by Ethereum. So the idea is to limit the number of validators. So therefore, anybody who want to be a validator needed to have something skin in the game, so to speak, avoid nothing at stake, and therefore greatly reduce the energy consumption. All right, so now let me go into problem formulation to see how this can be formulated. So some simple notation. So here I'm using K to denote any node or entity or individual or coin holders in the network. And a T is a time index. And throughout I'm using discrete time. And then the capital NT is the sum total of the number of shares at time T. Pi KT is the proportion of node K's share relatively to the total at time T. Now, the mechanism is that in each period of T, one additional share will be distributed. And every node K will receive a share with probability theta K. So theta K is the number of shares, the number of coins node K has over the total. The total be NT, but this is not a simple total. It's not NT itself, it is NT to the power of 1 plus alpha. So think about alpha as a non-negative value. So therefore, if alpha is equal to 0, then we are talking about the usual voting. If you have NKT, then this ratio NKT over the total number is your voting power, or the probability you're going to get this additional share. And with the complement, you'll get 0. So I talked about alpha equal to 0 corresponding to the traditional voting, which is a linear rule. Having alpha equals 1 basically coincides to what I said earlier about the square root voting. So in order to put down your NKT share into the voting power, the denominator is the total, not total, but the total squared. And of course, to be literally for square root voting, we should let theta be equal to square root of the number of shares divided by the total. But it turns out that doing the opposite, keep NT and then raise the power of capital NT is easier to analyze, cleaner. Mathematically, it's cleaner. All right, so recap. So pi k is the proportion of the shares. I will also refer to it as the distribution, share distribution. And then theta key is the voting power. In particular, in any time period t, this is the probability to get an additional share for any node k, and 1 minus is nothing. Now, if you look at the total number of shares, then obviously this is, every period, the total number will increase by 1 with this probability, 1 over NT alpha. That's because when you sum over all the pi k's, they equal to capital NT and cancel out another NT. So every period, the total number will increase by 1, and also the total number will stay the same with the complementary probability. When alpha equals 1, then NT process itself becomes deterministic. It increases by 1 every time period. So alpha equals 1 is the traditional voting. Alpha equals 2 is the square root voting. So for the rest of the talk, I will basically try to focus on alpha equals 1 because I'm talking about the square root voting, but the results holds for any alpha which is greater than or equal to 0, including equals 0, equals 1 as special cases. Okay, so here's a quick outline. Motivation, problem formulation, I already went through. And then for the rest of the talk, I will focus on the total wealth process, sometimes also referred to as the economy, Bitcoin economy, Ethereum economy, etc. And then also focus on the 2 sub-processes, the share distribution process and the voting power. In particular, we look at their limiting distributions, and then looked at the concentration inequalities and also anti-concentration inequalities. And in particular, I will bring out the so-called phase transition phenomenon. I will explain what that is. And then talk about some further research, open questions. As I said earlier, this is a very much ongoing work joined with Wenpin, and it's building upon his recent paper. I gave you the reference here. I think Wenpin probably has a paper posted somewhere you can read. And in Wenpin's paper, keep in mind, as I said earlier, alpha is equal to 0. So this NT process is a deterministic process, grows linearly over time. In Wenpin's paper, in fact, there are lots of other features which I will not touch upon. For instance, he looked at things like the so-called reward, which is basically the additional coin being created every period. The reward could be constant, it could be increasing over time, decreasing over time, etc. So in this in today's talk, I was strictly focusing on the so-called reward just being constant. And to be specific, just equal to 1. Okay, so I'm done with almost half of my talk. The other half will be just presenting to you the results and open problems. So I'd be happy to pause for 1 or 2 minutes to respond to any short questions.
There are no questions on
Okay.
chat.
Okay.
Maybe I'll ask a quick question.
Yeah.
Why is theta called the voting power? So the way you explained it is theta is the probability with which each person gets an additional share. Why is that the voting power?
Well, the terminology is very, I would say very tentative, informal. In particular, power, I realize power is probably too strong a word. It's basically the effectiveness of your share versus the chance you get the coin, gets the additional share. Yeah, but indeed, and even the distribution, the name is a little questionable. Lots of people think about the distribution as some kind of a distribution of a dividend, etc. But I'm talking about distribution purely in the sense of a proportion. It's almost more or less like a probability distribution more than anything else. Okay, so let me continue then. So the first object to analyze is this economy process or total wealth process. And as I said, for simplicity and also direct connection to square root voting, let's focus on alpha equals 1. So to refresh your memory, in this case, every period, the NT process can increase by 1 with this probability. Otherwise, it stays the same. So it seems like it's an extremely simple process, but when we try to analyze it, we went back and forth. Eventually, we settled down for this moment approach, basically just examining the moment. So the moment, in fact, is easy to analyze. By induction, we can very quickly pin it down. It's basically even order moments of this process is basically 2t to the power of j. And therefore, by this, very quickly, we can show that this nt square over t converges in distribution to x. And x is characterized by all of its moments. So therefore, we can conclude that x, in fact, is just equal to 2. So therefore, so this is the first result. So this anti-process converges in distribution to this square root 2. With additional work, in fact, quite a bit of more work, we can also get some kind of a large deviations inequality for this process. You know, more or less for large t, yeah, for large t, nt behaves like a square root 2t. So therefore, we want to also characterize what is the deviation from this square root t. So it turns out to be something like this. This is interesting in several ways. One is that the large deviation above this square root 2t and below the square root 2t is sort of asymmetric. This above this square root 2t decreases exponentially in t, and below it's only square root t. And another thing is that this second one, I mark it in red, turned out to be crucial in the later part of the analysis. We needed this result too. By the way, I trying to color mark the results in red if it involves lots more work. So therefore, other things not marked in red are relatively easy to obtain. Okay, so before I go on to study other processes involved, let me also point out another sort of interesting connection, which is to look at this ODE, this simple ODE. So very quickly, you see that inductively, you can establish that the solution is this. The solution is xt the power 2j is just equal to 2t times j. This is extremely easy to prove because the first step is just a trivial. And then if you assume this as induction hypothesis, you multiply this original equation by this. So this first equation is the induction hypothesis. And then the second one, you just put this in, and then immediately you establish the induction. And then you observe that this, after all, is indeed the moment, the even ordered moments. So in that regard, you can almost see this immediately, this equation immediately as what we would call in stochastic network a fluid model for this process. And this, in fact, is also a stepping stone to go from a 2 alpha equals 1 to the general case. For the general alpha, the result is exactly the same, very analogous to the alpha equals 1 case. So this is the general result. So if alpha is equal to 1, you go back to the earlier result I presented to you. Otherwise, this is the general result. All right, so now let's talk about the next process, which is the shared distribution, pi k. Pi k, as you recall, is the proportion of individual or node k at time t, proportion to the total wealth. So do the usual thing. What I'm doing is trying to verify that this pi kt process is a martingale. So you just compute this expected conditional expectation, break down into 3 cases. The first case is not any node win any share. Remember, in this case, every period is not like 1 share will be rewarded to anybody. So this is the first case. The second case is in a network, some node other than node k got the share, won the award. So this is the outcome. And the last case, the third case, is the node k itself win the award. So total number goes up by 1. K also goes by 1. So these are the 3 cases. So you simplify the 3 terms. You keep the first term. The first term is just going back to the proportion pi, and the rest sum up to 0. So therefore, this is a martingale for every k. So from a martingale convergence theorem, then you conclude that it has a limiting distribution. Okay, so now let me go back to Wenpin's original work. Wenpin's original work, NT being a deterministic process, increases linearly over time, leads to this familiar Polias N model, and therefore the limiting distribution can be explicitly characterized, Dirichlet distribution. Here, for the general alpha, we lost that. Only in that special case, we can claim that explicit distribution. So here, martingale is still preserved. The almost sure limit is still preserved, but we don't know, we don't have anything to say about the limiting distribution except the special case alpha equals 0. Before I switch to the next result, let me also, by the way, talk about this voting power. This is the terminology Siva questioned before. It's basically the effectiveness of share in order to bring in the probability of winning an award. So theta KT, you can do the same kind of conditional expectation, break down into 3 cases. First case, again, no node wins any share. The second case is other than K wins the additional share. And the third case is node K itself wins the share. So in that case, you can again simplify this. And in particular, in this case, you keep the first term, the second term, and then simplify the third term into this. And then you get this simple expression. And because this is the 1 minus 2 quantities, which are both smaller than 1. So therefore, we show that this theta instead is a super martingale. It's being a super martingale and also non-negative. Of course, it will also converge. But in this case, it will converge to, of course, 0 because of this, right? If alpha is greater than 0, then of course it will converge to 0. So again, it's not anything particularly interesting beyond the convergence. So this is basically what I said earlier in Wenpin's original work, focusing on deterministic linear growth NT. It's basically a Polias-Earn model, so therefore the limiting distribution can be explicitly characterized. Here, we cannot say much, so therefore we resort to concentration inequalities and anti-concentration inequalities. All right, so first, the concentration inequalities. To get the concentration inequality, we need the variance. Variance will play a big role, so therefore we need to look at the variance. So in order to derive the variance, it's fairly simple. In fact, you basically follow the same idea of breaking those into 3 cases, but look at second moment instead of pi itself. Okay, so derive and simplify the second moment. And then you take another expectation on both sides. And because pi k is martingale with equal means, so therefore the second moment quickly translating into the variance recursion. So you see the variance grows from t to t plus 1, and this is the additional increment. Okay, so repeat the variance formula, put it here. So the next thing is we want to bound this additional term. To bound this additional term, the first step is simple. It's basically trivial. Pi kt times this one is upper bounded by this. And then the denominator, you throw away n squared, just to keep n free, it also goes up. So the next one, I marked the red. So this is not so easy part. This is basically trying to claim that for large t, nt is basically this. And this is basically trying to get into the expectation. And that for that we needed this lower, the large deviation bound on the lower deviation part. That's inequality I previously marked as red. So making use of that, we can establish this for this part. So with this, we can now put this variance to the left, so therefore we have a difference. And then we telescope on the difference. We can very quickly bound this each one by the summation. This is basically the left-hand side is the telescope. The right-hand side is just a sum up of this expectation. and replace it by this term. So you get this. And then you further bound the difference, the summation by the integral, and then explicitly work out the integral, you get something like this. Because we are concerned with large T, so you can throw away this term. All right, so this is the result. So it says that the variance of a pi k is basically the order of a pi k 0 over n 0. And then apply Chebyshev. So you can get this. This is the kind of a concentration we're looking for. This ratio deviated from 1 exceeding from epsilon is now less than or equal to through Chebyshev. You put this into the Chebyshev formula, you get this. And then this one basically says that when n0, when we have a large number of shares, when n0 is large, then this right-hand side will go down to 0. Meaning that if we are talking about k, the initial share is this order, is fn0. fn0 goes to infinity as n0 goes into infinity, which basically says that node K is quote unquote a large investor, a large shareholder, proportional to N0. So in this case, this large shareholder's share over time, including going to limit, this share will approach 1. So it's basically stable. It will not get infinitely richer, and it will not go down either. So it's a stable. This ratio is going to 1 as the limit. And this, in fact, concentration property holds for all alpha, not just alpha equals 1. All right, so how about the other way around? How about the smaller investor shareholders? Suppose NK0 is constant, 0.1, or rather this share of the initial of the node K initially is order of 1 over N0. So if you think about there's a total of 1,000 shares in the entire network, then this shareholder is basically holding order of 1,000. So in this case, we can strengthen the previous result such that pi k 0 over n0 not only is the upper bound of this variance, it is also a lower bound. So therefore, this is the same order. And then making use of this variance, you can very quickly conclude if NK0 is equal to, if it's in this order, or initial share is order of 1 over N0, and then the variance of this ratio is, instead of, in a previous case, it will be equal to 0, right? Because the ratio will approach 1. In this case, this variance will be order theta 1. And similarly, if you go down to you can think of this as intermediate shareholder. This is not the big ones, it is intermediate. And then you can talk about a really small shareholder. Initially, their share is high order, little o of 1 over N0. Then you can verify that the variance of this ratio will go to infinity. So both of these suggest that for the intermediate or small shareholders, the result will change. We will not have this share ratio being stable in the sense of approaching 1 as the limit. So this is the result, this so-called anti-concentration inequality. So the concentration inequality now turns into something like this. The left-hand side is the same as the concentration inequality. It's the same statement about concerning the ratio deviated from a 1 exceeding a positive epsilon. What is this probability? Previously, this probability will be upper bounded by a quantity on the right side, which goes down to 0. Here, it's the other way around. This probability will be strictly greater than C, and the C is a positive constant. Okay, so this is the kind of this anti-concentration inequality we want to establish. And to establish this, in fact, the amount of work is much more than establishing the concentration inequality. And that the reason is because we want to bound the variance from both above and below. So therefore, we needed to go into higher order moments. We needed to go into the fourth order moments, centralized moments. And this is again sort of a result that requires more work, marked in red. But at least it's intuitive. The fourth moment is order of 1 over n04, which in a way is intuitive if you look at this. If you look at this variance, pi k0 is order 1 over n0, so therefore this part is 1 over n0 squared, and the variance is essentially the second order moment. So for the fourth order, it's still the same spirit, but as I said, the proof involves more work. Okay, so this is basically what I refer to as phase transition, or rather the phase transition is the term used in Wenpin's earlier work. Wenpin, by focusing on the Polias-Earn model, established this kind of a phase transition. Large shareholder, the share ratio is stable. It will converge to the limit of 1, basically stays stable over time. On the other hand, the intermediate and the smaller and the small or tiny investors, the same cannot be said. The ratio will deviate, will definitely change, not being 1. Furthermore, in Wenpin's earlier work, there's much more being revealed. For instance, through the explicit distribution, he showed that for the intermediate shareholders, the limiting distribution is basically a gamma distribution. And then for the further down, the tiny shareholders, this is the little o of 1 over n0. You know, their share will basically be wiped out, going down to 0. But as I said, unfortunately, if we go beyond alpha equal to 0, these additional facts will need to be further pinned down. As of now, we don't have those results. We only have those concentration and anti-concentration results. So this is a quick summary. The kind of results we have obtained are a statement about the total wealth process, convergence in distribution, plus that large deviations results I showed you. And then we have a shared distribution, converges almost surely, but the limiting distribution, we don't have much to say except the concentration inequalities and anti-concentration inequalities. Specifically, we have established that for large shareholders, in this sense of the initial shares, the share ratio will converge in distribution to 1, and the small shareholders, in this sense, or theta 1 or below, it will be the anti-concentration, meaning that with positive probability, it will deviate from 1. So the positive result is that the so-called phase transition applied to both cases, alpha equals 0, and also alpha strictly greater than 0. I can pause for 1 or 2 minutes before I talk about the open research.
Maybe I have another quick question. Yeah. So how does this this dynamics that you analyzed relate to proof of stake in blockchains?
Relate to what? Sorry.
Relate to proof of stake model in blockchains.
Oh, great question. Proof of stake, as you recall, is basically the case of alpha equals 0. That's the case Wenpin studied.
Okay.
But on the other hand, this being essentially a consensus scheme or voting scheme, there's nothing to stop people go beyond to some general alpha. Okay. It is conceivable in the future to consider alpha take on other values. So therefore, certainly we want to at least throw out the kind of possibilities for alpha not equal to 0, beyond 0, including alpha equals 0 as a special case. And this probably is also a great time to jump into the last topic, which is open research. In addition to the
a couple more questions.
Actually. Yeah, sure.
Fernando and Barnaby. So Fernando, please go ahead.
Sorry.
Thanks. Hello, can you hear me?
Yeah.
Yeah. So no, the question was in the case of small investors, you mentioned the deviation from the initial condition. Do you have any idea whether it moves up or down, meaning they gain share or they reduce share?
Both. The answer, quick answer is both. But for the quote unquote tiny investors, the eventuality is wipe out. Okay. But on the way, it's remember that ratio has variance which is infinite. So and in Wenpin's original work, you know, with this gamma distribution, that's not for the tiny investors, tiny shareholders, it's for the intermediate ones. There's even some possibility to pin down the probability of gaining shares and also the probability of losing shares.
Thank you.
Yeah. Yeah, that's why I said that there's some further work to be done, see whether we can get more results for the general alpha case, something like that. Okay, so I mentioned earlier about this fluid model. So this is what I call the fluid model. And the obvious thing to keep in mind is the diffusion counterpart. So which is to add in this Brownian motion part. So in this case, A and B are two constant parameters. So this is anybody who's familiar with the Bessel process, you recognize this is basically defining the Bessel process XT. And the Bessel process itself has this you know, so-called phase transition phenomena, depending on the choice of A, B. So that's certainly one direction to pursue. And for those of us working in stochastic networks, you know, again, this is sort of a natural next step because, as I said, this corresponding to the fluid limit, fluid model, and this corresponded to the diffusion model. So now the question is, NT per se won't fit because NT itself has is increasing over time. So therefore, we need to do something like a centering, and perhaps to include some sort of a scaling as well. And also, for me, it's striking that NT, without anything else, this square root T already came out. And remember, in diffusion scaling, the space scaling is exactly a square root. So I think that this is a striking similarity, but how to exploit this to push this further requires definitely more work. And the other thing is that analogous situations to stochastic network is also sort of all over the place. Certainly for somebody like me, having worked almost my entire professional life in stochastic networks, you start to see this kind of a phase transition. As we all know that in the stochastic network, eventually the node is separated into bottlenecks versus non-bottlenecks, so that eventually you only need to focus on the bottlenecks. And very much this is a similar, the phase transition phenomena is that the large holders, you can focus on their distribution. The other ones, the tiny ones, will be wiped out eventually. But of course, the past or before what happens, that's also of interest. And those are perhaps new phenomena, not in stochastic networks. All right, so I guess I stop here and see whether there's any final questions.
Let's first thank Professor David Yao.
Thank you.
And feel free to ask your questions.
Hi, should I ask my question now?
Please go ahead, yeah.
Thank you, Professor Yao. It was very interesting. Earlier, you said that nothing prevents a proof-of-stake protocol from adopting the square root voting rule or even alpha greater than 1. But there's maybe one thing that prevents the protocol from adopting it is the Sybil resistance problem. So if I am a staker in this protocol, and I know that the square root voting rule is in place, what I want to do is split my stake between many different nodes so that I can increase the probability that I win the next share. So I was wondering if you had some thoughts about this question.
Yeah, excellent comment. That's part of what I had in mind when I had this first item about the future research, the so-called resource pooling, division of job, and all that. And indeed, what you said needed to be studied. What if several nodes pool their resource, which already happened in proof of work, and also you can do division of job. Whoever does validating the longest chain need not be the shareholder. You can sort of designate somebody else to do the work for you. You put down your share, somebody else do the work. These are all possibilities. And what's their implication on the dynamics of those processes, in particular share distribution and also voting power, that remains to be studied. Great point.
Thank you.
Yuan, go ahead.
No, as a small question. I'm not terribly familiar with the mechanism of this blockchain, but I'm wondering, the model assumes the number of voters is constant from the start, right? The capital K is fixed. I'm wondering, in reality, is that does that grow with time, or does that fluctuate over time?
That's also a great point. And in fact, in Wenpin's original work, it has many features beyond what I just said. And indeed, Wenpin examined that question. The number of nodes relative to the number of shares, etc. He studied both cases, like a K being fixed, or K may also grow, etc. So, indeed, there's some fairly intricate relation between those things. Yes. It's a great point.
Thank you.
Yeah, but I would say, dig up Wenpin's paper. I'm not sure whether Wenpin is still there. Maybe Wenpin should add something.
Okay, I'll go look up his paper.
Right.
Thanks, David.
Sure.
I have a question about the Brownian approximation. So you mentioned how, like, with the fluid approximation, you get the square root of descaling, but then your concentration results show that the fluctuations above and below are of different scaling. You have like e power minus t and e power minus square root of t. So has this been studied? Like, have these kind of models been studied in stochastic networks literature in the past?
No, not at all. That, I think, is the thing I found striking. And I must give Wenpin credit for that. This is something I did not know before, certainly not in stochastic networks. So that's why I was further intrigued by this model having so many things I'm familiar with, but on the other hand, some things are very foreign.
That probably makes the whole analysis extremely challenging, right? The fact that the scaling.
Exactly, right. That's another thing. You have to settle for the convergence in probability in distribution. Yeah.
I see. Got it. Okay, if there are no other questions, let's thank Professor Yao again.
Well, thank you. Thanks to all. Hi again. Good seeing you.
Nice seeing you all. Our next SNAPP seminar is 3 weeks from now. Bye.
Thank you.
Thanks a lot, Professor Yao.
Thank you. Siva, would it be possible to get a list of participants if it is not violating any privacy issue? I didn't have a chance to go over.
I see.
Who
I'll look into it. I don't know how to do it.
Yeah, but it's okay.
I could see it during the talk, but I don't know.
Yes, same thing. I sort of that's the thing I don't quite like about doing things.
Yeah,
like
I know.
I don't know who are my audience. Right.
Yeah, I know. Yeah, I'll look into it.
If I
manage to find it, I'll send it over.
Yeah, thank you. But I assume anybody who really shows interest may contact me.
Yes.
Okay. Yeah. Thanks again.
Bye.